Our next speaker is Shie Mannor. He graduated at the Technion, where he's currently a professor. He was previously at McGill. His research interests are planning and control and network.
So I know that I'm standing between you and coffee. So as you see, my affiliation is both with the Technion and with Ford. And today I'm going to tell you about how I think we should solve real problems, and how hierarchical RL is really the key to solving real-world problems. So I'll start with saying a few things about hierarchical RL. So flat RL, which is what we sometimes call black box RL, is something that works for either very small problems or with huge amounts of data. We do want to scale up to solving complex problems. And you think about self-driving cars as the problem of the day. I think that it's very important to understand that humans don't think at the granularity of actions. And we really need explainability, and we need semantics. And one last thing that is interesting is that hierarchy can be thought of regularization. So what we're going to talk about is why HRL is the key to solving different problems, and we'll talk about different aspects of HRL and how it can really help save the day. So the main goal of HRL is to scale up. So it's really not about, at least from the engineering perspective, not about understanding a problem, but about solving a problem. So how do I decompose the problem to many small ones? A side bonus is transfer. So I want to be able to share or reuse knowledge that I acquired. And there are really three key ideas. So you can think about it as if I'm imposing constraint on the value function, or that I'm building algorithms that take constraints into account. But what I'm going to talk about today mostly is about how do I encode domain knowledge into hierarchical RL. But let me start with a picture. So this is this is something that happens. So we do, when we'll have self-driving cars, we'll need to be able to explain how that thing happens. So explainability is really the key. And this is in some sense a call to arms. So I think that RL and our field, as in general, has been shying away from solving real problems. And from my experience in the last few years, I think that RL will not be implemented in many interesting domains, especially not in healthcare, not in industry, 3.0, 4.0, and certainly not in self-driving cars. It's just not, the regulators are not going to allow it in most countries. In healthcare, certainly, I think that this is a field that is ripe for the taking, but if you'll have black box RL, I wish you all the best in trying to convince doctors to actually use it in practice. So it's really about trying to understand what is really happening and how to explain what we're doing. And this little picture here shows how things are happening today. So basically, this is a supervised learning system. I run things through it, and then I don't really understand what happens. I don't understand why it said what it said, and I'm just hoping for the best. In the future, there are really two approaches how I will approach it. So whether there will be tools to interpret what the black box is doing, and those tools will have to have approximately 100% coverage, or that will just build algorithms that are explainable and interpretable. So before we talk about HRL, let me just give you a little bit of taste of options and whether options occur in nature. And for that, mind my pun that's about nature. For that, this is a breakout. And what you see here is that we see this is from the famous Atari paper. And we see here the breakout TSNE produced by a paper with my students. And what we will see, this is the TSNE of the last layer of activated, the new DeepQ network that is activated, and I think it's three-dimensional, and high value is in red, and low value is in blue. And what we discovered is essentially options are discovered by the network implicitly, even though it doesn't say so, and even though that DQN is supposedly a black box algorithm. What it's really doing is it is discovering options. And there you can think about state aggregation and about skills within the framework of options. So the basic model is the MDP model. That's the model that we all care and like. But then once you identify skills and you make it into a semi-MDP, that's a highly temporal hierarchy, meaning that you take your model, and instead of having single ticks, you have multiple ticks. Sorry. And then the other approach would be to go through state aggregation and do spatial abstraction, so spatial hierarchy. But what you usually do is we go straight to what's known as an SAMDP, the state aggregated and skill identified MDP, which has both. So basically, when we think about problems, often what we do is say those two states are kind of the same, so let's view them as similar states. And we are currently taking a long action, and let's view that as a single action. So in our minds, at least I believe so, what we're doing is both temporal and spatial aggregation. To show just the difference, here is just an example. So an MDP is just basically your many steps here. And then the semi-MDP, you're taking longer actions. In an aggregated MDP, you have regions where are sort of regions where you're doing something similar, and then eventually in the both semi and aggregated MDP, you're doing both temporal and spatial abstraction together. And going back to the breakout example, so when you look at breakout and you ask what is happening there, so what we see is that there is this sort of banana curve shape, and basically the optimal policy in breakout is to cut a tunnel on your left or on your right. This example is on your left. Once you cut a tunnel, then you start killing all the bricks one by one, and you can do it quite fast. So to make a long story short, what happens for the optimal policy that it goes in this direction, like this. And basically it digs a tunnel on the left. Those are states that you see in the silencing map where you do it on the left. And then you have more bricks, and you start eating more bricks, until essentially you're left with nothing. So what we see here is that basically a black box algorithm, and I would say a very black box algorithm even, is really using hierarchy or temporal as abstraction to do something useful. So we see that options do occur not only by design but also by chance. So what are options? So options are a way to combine a sequence of actions in a non-trivial way. They've been called skills. They've been called macro actions. So they've been used in the community for quite some time. Actually, it's good. People can fall asleep. So and there are several questions. One of the questions is how to identify useful action sequences and how do I find options. I think that's not a really important question. I think that if you have a problem that you really want to solve, you're going to solve it. You're going to invest the time, the money, the people to do it. Think about self-driving cars. If I want to solve it, I will invest people in figuring out what is an overtake and how to overtake. But a question here which is perhaps more interesting is how do I encode prior knowledge? And I do have lots of prior knowledge in these problems, and I do want to encode it, and that's what we're going to talk about today. And the theme of this talk is control of complex tasks is really an inference problem where I have to choose between the available options and modulate them, meaning I have to give them the right context. So let's start with an example before we talk a little bit more formally about options. So this is, I think, a pretty famous example from the early days of abstraction. And this is a reconnaissance mission planning. People are talking about lots of planning problems. When you try to do robotics or self-driving activities, you do a lot of forward planning. In this example, you have limited fuel, and basically this is known to be a very quickly, very intractable problem, and this is a problem that is solved every day by each of us, or similar problems are solved. So what we see here is that there is an abstraction here. The abstraction is done automatically, And if you'll have to tell to yourself, how did you plan to come get in this very cold morning from your hotel room to this lecture hall, then I'm sure that you've done some planning. And this is, and hopefully each of you took a coat, because the context is it's a very cold day. So what I'm trying to say that when you're solving a planning problem, or when you're solving a learning problem, there is a context in the back of your mind and you're using it constantly. The question is how. So before we go to the how, let's talk a little bit about options. So options, this is a classical framework in HRL. It's the formal definition of an option is that it's a triplet, the starting states, the policy itself, pi, and the termination condition. There are other variants that I'm not going to talk about with a little bit more complicated aspects, but basically that you know where you start, you know where you end, and you know what you're supposed to do. That's what options are, and note that pi itself can be fairly complicated. So nobody is telling us where the policy itself is coming from. It could come from someplace which is, it could be hand-coded, or it could be learned. There is one interesting view here that there is a dual view for options and semi-MDPs. So usually there is an underlying MDP, which is basically tick-based. So you have a tick. If you have say a driving application, it could be 100 milliseconds. If you have a robot, it could be even less. So you have a tick that is regular, and this is discrete time homogeneous. And then you have a semi-MDP, which is a continuous time discrete event process. And when you overlay the options on the process, it really looks like there is both an MDP interpretation and a semi-MDP interpretation, and you can choose whatever you like for the problem at hand that you're trying to solve. So basically, both approaches are interesting, and what you can do is you can use you can look at the value function. So you can have the value function in terms of just the actions, and you can have the value function in terms of the options. You can have option optimality and action optimality. Option optimality is usually weaker. So the optimal policy itself, of course, will be composed of actions, and there is no a priori reason to believe that option optimality is going to be even close to action optimality. So that duality is something that confused researchers for quite a while, I think. And because we like to have things that are optimal, we focused on action optimality. My claim is that action optimality is not really interesting. What you want to have is you want to have option optimality and robustness to changes. But before we get to that, let's talk a little bit about why options are good. So the first reason is that it gives you fast exploration. So this is sort of a simple example. So if you have options, basically you traverse the space very, very quickly, and you get fast exploration. So this is interesting, but not too much, because I don't think that you're going to get to do much exploration on real problems. I think the more interesting result is that of fast inference. So a few years back, with Doina and Timothy Mann, we showed that when you're doing planning and you have options and your convergence rate is much faster, in fact, it's governed by the average discount rate. So if I have very long options, I'm going to converge much faster in the planning itself. And this has nothing to do with the learning. This is just pure inference problems. So let's go back to the dual MDP, semi-MDP interpretation. So basically, I don't know what options I'm really supposed to do at any given point in time. And what I could do is I can use one option and learn about another, and that could be actually fairly efficient. We call that intra-option learning. So learning what one option is doing while exercising another. That can be done with off-policy technology that I think will be discussed shortly after the break. So intra-option learning is cool. It's something that we can do when we observe other people. This can be something that is related to transfer learning, to imitation learning, but it's everything boils down to the same concept of I observe what other people or someone is doing, and I learn from it. You can do it with Q-learning. You can do it with policy gradients. GTD, and so forth. So intra-option learning is the key because I will normally have many options to choose from. So let's talk about why I should use options. What are the advantages? So first, I want to believe that there is a chance for transfer. That's sometimes the case, and sometimes that's not. But once you have, if you can do transfer, then you can provide the domain knowledge in terms of options and sub-goals, and then you can transfer from one problem to another. Options are much faster, and they represent your knowledge in terms of in an expressive, in a clear manner, and you can use both learning and inference from them, as we saw in Sergey's talk. But the most important thing is you can learn and plan rapidly, much more rapidly than in other using atomic approaches. Just think about trying to look five seconds into the future in a driving situation. It seems pretty difficult with atomic actions, while not so difficult with options. So, however, options are not a silver bullet. The choice of options is difficult. Sometimes if you don't understand the problem well enough, then we don't know how to choose them. For me, this is not such a big disadvantage, because I think every problem that is really worth solving, you will invest the effort and time to build options. Options are rigid, so once you code them, you're not sure how to actually use them, and you're not going to change them because a lot of time and effort is invested in them. And also there is a potential for negative transfer. So when you start with something that looks good but is not really good, sometimes it's really going to be very hard to change. But the main issue is that you need to figure out which option you're going to use and when, and that's really the crux of the matter. So should you use options? So the short answer is sometimes. The only real reason to use options is once you have prior knowledge. So it really options and hierarchy in general, for me, is really about how to use prior knowledge effectively. You can use it for transfer. You can use it because there is a context and you want to use a context, or because you want to understand, or you think you understand, the state or observation space. And it should be a caveat that everybody should know here, that options are not always going to help you. If you don't understand the situation, you don't understand the problems, looking for options is not going to help you very much. Okay, so I will talk about 3 ways that options can help you, and then I'll briefly mention 2 others. The first one is situational awareness. So you see the guy over there, he looks pretty happy. He doesn't know what's coming. Whoever, if you've ever driven in a country other than Canada, that also happens on the road. So understanding some other driver behavior can be an issue, and you want to understand the context of a problem. So let's just look at understanding the context. So this is a simulated soccer match. When I'm losing, there are 3 players here, so I'm going to pass the ball as fast as possible to the player that is in the scoring position, and then this player is going to shoot and try to score. So when I'm in a losing position, I'm going to score as quickly as possible, but when I'm winning, I'm going to keep a possession. So I'm going to just pass the ball between the players and hope that nobody is going to interrupt the passes. So the game is the same game, the players are the same players, but the options or the hierarchy should lead to that in the context of winning or the context of losing, I should focus on different actions. So this leads us to the architecture for situational awareness. So basically, I have here multiple options. There are options that are either pre-coded or that they're learned. At any given time, one of the options is executed. The question is which one, and there is a policy learning thread that is what you can think about as an inter-option policy. And inputs can be things like time, space, endogenous or exogenous factors. Exogenous factors can be things like weather. Endogenous factors can be things like what happened to the agent recently. And I should mention that the awareness parameters are also going to go into the options, not just to the policy learning architecture. So this is a situational awareness architecture, which I think is pretty useful and it has been used successfully in several applications. And this leads to what's known as the option-critic architecture. So here we try to do everything. We try to both learn the options and the policy over the options. And it doesn't really matter what is the algorithm here. You can think a bit about the actor and the critic as deep RL algorithms, but the depth here is not really important. I should mention that you can think about the new model called contextual MDPs. So in contextual MDPs, there is a context. The context is either static or quasi-static, meaning that the context does not change much and certainly does not change often. And certainly we have no effect of it. So think about it like the weather. When I'm driving, I have little effect on whether it's going to rain or snow in the next few minutes. But that's the way it is. I mean, snowing or raining is not something I can really change. So the real issue is, here is what are the right variables and how should I parameterize the options? And the claim is that it's very difficult to do. Basically, this is the same example that we had before. The soccer, when I'm losing, I'm going to try and score as quickly as possible. So I'm going to basically pass and score. When I'm winning, I'm basically wasting my time, going to the midfield, maybe walking a little bit, talking to the referee, just not doing much. I'm sure whoever here saw a soccer match saw it quite often. So the issue about context is that you need to parameterize it somehow, and how to do it is not always obvious. But there is one thing which is obvious, is that sometimes you can make by with understanding the observation space. So basically, in this case, you want to do what's known as skill partition. So skills are specialized across a space, and you train different skills for different parts of the input space, or the state space, or the observation space. And this leads to what we call skill adaptive partition, which is an instance of the option-critic architecture, where the box here of policy over options is really a partition of the state space, and you can solve it. You can use gradient algorithm. You can do the math here. The math is not too exciting. You can get an algorithm that iterates between policy gradients for the policy over option and for the option policy itself. But how would you encode prior knowledge? Prior knowledge can be encoded in the shape of the regions. So here in the example, we have a dribble area and a score area, and because we're using ellipses, and this is the kind of area that we got, and you can have different types of regions to partition the space. And the main point here is that you need to know something about the problem. If you do, then you can use this knowledge on what are the shapes of partitioning the space. And this is just an illustration. You can do, of course, something which is much more complicated. So we saw that you can use context and that you can partition the input space, but there is something which I think is even cooler. So basically, sometimes you don't know what your model is really like. So the example here is an acrobot where the length of the arms is different. So it's slightly different. And I want to do well enough on all of them. So I think that I'm going to get a robotic task. And those tasks are going to be kind of similar, but probably not exactly the same. And I don't want to rerun my algorithm. I don't really know what to do. I just want to solve the damn thing. So the question is, how do I do that? And just to give you an example of things which you can do, which I think are kind of cool. So here's an acrobot and cartpole together. Both of them have a different range of parameters. So the weights differ here, and the length differs here. And basically, you have two options. Whoever is familiar with that, this is the state space. So this is the speed, and this is the location. So theta dot and theta. And you have two options, and you can try to train a DQN with a range of parameters. So basically, give the DQN different values of the cartpole and the different values of the weights. This is going to end up in a disaster because DQN is made for a single parameter. Or you can try to train what's known as an option DQN and just try to duplicate the last layer. This is also not going to end up well because both algorithms assume that there is a stationary environment and that things do not change much. So even if you're going to give them many trajectories, it's just not going to help. But there is a solution here which is pretty cool, and you can use what's known as a robust TD update. So those are the classical standard TD update. The main difference, I'm showing it for the TD in actor-critic type algorithm. The same would go for DQN. Is that here you have some infimum over the distribution probability within a given set. So what you have here is that you have some knowledge about the problem or about the uncertainty of the problem, and you're using it to create robust options. And just to show the results, so this is a graph which is a little bit different than what you used to see. Here we have the pole length, and here we have the R mass. And this is for card pull, and this is for Acrobot. And we'll look at the average reward for different algorithms, and we see that basically, if you're doing DQN or option DQN, your algorithms collapse. And while if you do the robust option DQN, then things still look pretty good for you. Your performance do not deteriorate much as the parameters change. So in this example, perhaps surprisingly, what I have here is that my prior knowledge is an uncertainty model. So I know what kind of problems I'm going to solve. But think about driving. I know what's the right pressure in my tires. This pressure is not going to change much, but it can vary from one value to the other, and I still need to perform well for all those values. So I'm doing policy evaluation, and then I do the robust policy gradient, and this is how I use my prior knowledge. So to conclude, as I said, I know that I'm holding you, I'm standing between you and coffee. So options encode prior knowledge, and for me that's the greatest value. You can encode it by the options themselves, by waypoints, sub-goals, tasks. There are different names for the same things. So you can code them different ways. You can encode your prior knowledge by saying what are the important inputs, what is the risk attitude. You can partition the state space or the observation space, or you can encode the uncertainty model that you have. What I didn't discuss today, the issues of interruptibility, and transferability. Interruptibility means that I know which options can be interrupted and how they can be interrupted. This is something that is essential for every real applications, and also in terms of transferability. So how do I transfer information from one task to the other? So for me, the control problem in structured learning is which option to use, and also why. So with that, I would conclude. Thank you.
Thank you, Shai. Any questions? None? Okay. Yeah.
Hi, thanks for the talk. So it seems to me that options is a sort of a finite discrete set that you have to choose from. And I'm wondering if there's a middle ground where options are more soft, whereby you don't need to choose the number of hierarchies or the number of options, and you can maybe learn them in a smoother manner.
So thank you for your question. So there are parameters options, which we often call them skills, in the jargon of the community. So they're parameterized by usually very few parameters. Think about 2-3 parameters at most, and they allow you for a smooth, a relatively smooth interpolation between different things.
Let me ask a question, because in the definition of options, you emphasize that there's the initiation set.
Yes.
Isn't that the responsibility of the meta controller to decide where to call an option?
So that's a good question, and the answer is not clear. So sometimes it is, and sometimes it isn't, based on how smart the option is. So think about options as a small piece of code that is doing something trivial. I think that's not the case at this point in time. Options can be fairly complicated systems that on their own, they do things, and they actually are the one that are calling the shots. think about ABS braking system. So when it's time to use ABS, you want it to activate. You don't want it to start to negotiate with your car whether now is a good time to brake or not.
That's a good answer. Any other questions? All right, so let's thank Shie again.